Okay, so a couple announcements. The midterm one, the grading guidelines are now online. My apologies for taking so long to get around to doing it. I'll actually show you where it is in a minute once I finish with the announcements. Once you have your exam, you can look at the grading guidelines which are online and fill out an exam regrade form. And the exam regrade form looks kind of like this. I have a whole bunch with me. Somehow attach it to your exam. Staple is preferred. If they are loose, then they'll get separated and you don't get your regrade. In particular, a regrade is if, for whatever reason, we did not follow the grading guidelines for your exam. If we took off too many points, took off too few points, if you feel the grading guidelines were unfairly harsh or I'm a horrible person for doing it and somebody needs to feel your wrath, come see me during office hours. This is not the way to actually vent your wrath about the grading guidelines per se. It's just a way to make sure that we have, 20 TAs that are grading this, in case there are any inconsistencies, that they are as minimized as possible. Actually, I'll show that now. So if you go onto the course webpage, which I conveniently have loaded up here, on the exams page, these links right here, let's try that again. The first midterm, the grading guidelines, and the regrade form, and you can all go about looking at said grading guidelines, loading up the midterm, et cetera, et cetera. So that's where all that is hidden up on the website. So we're catching up with grades. We fell a bit behind, both because we wanted to get the exam grades returned to you as fast as possible. Then spring break hit, and everybody went on vacation, including myself. Well, I didn't go on vacation, but the TAs did. So we're working on catching up on the grades. We currently, the quiz 1 I expect to be returned by the end of the week. Hopefully homework 4 as well. The 5th homework, that's the game of war, peace, and that's out. It's due this Friday. There will be a 6th homework out. That's going to be out by, we'll go over it this Friday. It's due the following Friday. So this week and next week are classes as normal. The following week is going to be the second midterm in the Wednesday of that week. So 2 weeks from 2 weeks and 2 days is the next midterm. I'm going to be out of town on Wednesday. I'm actually between 2 conferences, and I came back actually to teach classes today, but unfortunately I won't be here on Wednesday. Professor Tom Horton will be teaching class here just as normal, and he's going to pick off right where I left off. So there will be class on Wednesday. You're just going to see somebody else other than me talking to you. So not surprisingly, I'm not going to have office hours because I'm going to be in Charlotte, so I can't really hold office hours. Clickers. We're going to start using clickers more seriously now that spring break has ended. I have a couple slides that I'm particularly interested in using clickers on. If you don't own clickers, you need to go purchase one, and we'll start using it in class. There will be grade penalties ensuing for those who don't have clickers. You also need to register it. In particular, when you register it, R4WRCRF01. That is not your serial number. That's actually the product number. Everybody's clicker says that number. If you are having problems finding your product number, I'd be happy to take a look at the back of your clicker and figure it out. We're going to be going over something called the halting problem today, which is an extremely important problem both in computer science and for this class. It is not in the textbook. It's some additional material I'm including. It makes for great test questions. We're then going to be starting Chapter 5, which is methods. And we'll be moving through Chapter 5 all of this week and probably the beginning of next week. Questions, comments, concerns? Okay, so this course has a bit of a interesting problem in that the goal of this course is to teach you a lot of programming, but I want to start showing you some of the more interesting parts of computer science. In particular, computer science is all about problem solving, about figuring things out. And so there's a number of sort of theoretical things that I plan on introducing in this class, and the first of them is something called the halting problem. Specifically, as you're going to see in a minute or two, we had to wait until we actually saw loops before we actually got to the halting problem. Why is this? Okay. So, given this class and the main method. What's wrong with this? And it's a bit of a rhetorical question. You'll notice that, well, if you can't figure it out from reading the class name, once you get into the main method, while true, system.out.println. And obviously, true is always going to evaluate to true. So this is going to loop forever. In this program, when you run it, it's basically going to print out an infinite number of returns until you close the command window or do something. So this is an infinite loop, where the program is stuck looping forever and ever. And we have seen this many times. When you use Windows, for example, every now and then, maybe like once a day, it just decides to hang, or various applications decide to hang. And no matter what you do, they just get stuck, and you can't do anything to them. That's a infinite loop. And the problem is that we don't want programs to be stuck in these things, because this doesn't really do much other than, take up a lot of resources. And the question is, given a more complicated program, more complicated, I mean more than, 3 lines, something like, the program you use on Windows, can we actually figure out if it gets stuck in an infinite loop, or if it somehow finishes appropriately, it exits or halts, hence the halting problem. And I'm going to further refine what the halting problem is exactly, but that's basically the essence. Given some program, how do we know if it ever halts, if it exits? Maybe it gets stuck in an infinite loop, maybe it doesn't. So we also saw this example from the first slide, right? Gently massage shampoo into wet hair, lather, rinse, repeat. That's obviously an infinite loop. A human understands that, probably shouldn't spend forever inside the shower washing out the hair, but a computer doesn't. Right. And that, of course, is a photoshopped image because I went to CVS and no shampoos actually said this anymore. So the halting problem is defined as such. Given some program P, however you define P, just pick some program, I'm going to call it P, and some input I. I is the input to the particular program. Maybe it's input that the user types into the keyboard. Maybe it's a file that's read in from the disk. Maybe it's data that's sent over the network. Maybe it's something that comes in from a scanner. It actually doesn't really make much difference. But somehow, it's some input that the program reads in. So I'm going to say that P is going to be a file name, a string file name for some Java program sitting on a disk somewhere. And I is also going to be a file name for some series of input sitting on a disk somewhere. And we're going to run that Java program P with that particular input I. And the question is, will this ever terminate? Will it go forever and ever and ever, meaning will it loop forever, or will it eventually halt and finish as we'd like it to? The question is, can a computer actually figure this out? Can we design a computer program to figure out whether another computer program will ever halt or will just loop forever? And of course, the next question is, can we actually have a human figure this out? And I'm going to show a bunch of examples that talk about this. So this was first shown by Alan Turing in 1936. He first discussed and published on this. I'm kind of avoiding exactly what he showed, and I'll get to that in a minute. But the interesting thing is that he showed this 10 years before computers actually existed. So to solve the halting problem means that I have some class Oracle. Oracle stands, I'm going to get to Oracle in a second. And in that Oracle class, there is a method called checkHalt. And what that checkHalt method does is it takes in some P, some string P, which is a file name, and some string I, which is some name of some input. And it will return either true or false, depending on whether it loops forever or halts. So I'm going to assume, for the sake of this lecture, that Oracle is some class that always returns truthful answers. Now, obviously, we can't always get truthful answers as much as we'd like to, right? Predict future, get next lottery numbers. There actually is, and as we're going to see, the concept of an Oracle, or you'll see if you continue on in computer science classes, the concept of an Oracle really makes a difference. If you are given the right answers, can you tell they are the right answers? Because before we actually figure out how to get the right answers, we have to figure out if we could tell if we got the right answers. So I'm going to assume, for sake of this argument, that there is an Oracle class that always gives right answers, and there's a checkHalt method. Right? P is the file name for the program. I is the file name for the input. And it will return either loops forever or halts. And actually returns it as a Boolean, right? So true means it loops forever, or false means it halts. And that's all it does. How it works, I'm going to ignore, and we're actually not even going to see in this lecture because it doesn't actually matter how it works. But all it does is take in a file name of a program and a file name for an input, and it tells true or false whether or not that program with that input will loop forever or will eventually halt. Okay, how many people feel they're good so far? Okay, I'm seeing most hands. In particular, this must work for any Java program. We can't just say it's going to work for a couple subset of Java programs or programs just with print lines. Basically, it has to work for any Java program. And that's what the halting problem is. It can't just work for a couple few programs or simple programs. So, taking your best guess, do you think it's possible to solve the halting problem? And I'm really interested in what your best guess is. There's no right or wrong answers, really, as far as I'm concerned for this. So please try to guess what you truly think, not so much, what you think the answer is. Ah! Oh, crap. All right, hold on. I want you to know that the whole reason that I got the clickers like this, I've been waiting for this to use the clickers. And if it doesn't work, I'm going to call and vent my wrath at the clicker company. Please stand by. We're experiencing technical difficulties. Come on. So, as a real-world example of why we actually want the halting problem. Yeah. Hey! I was here, and participants auto. No, auto. Oh, you're kidding. Wait. Okay, now it's working. Yes. Okay. So 61 say yes and 23 say no. Okay. So anytime we're trying to figure out how to tell a computer to do something, first we have to figure out how a human would do it. You and I, if we're going to program a computer to do something, we need to figure out how to do it first before we tell a computer how to do it. For example, when we were doing, what was homework 1? It wasn't Windchill this year. Whatever homework 1 was, that particular formula, we need to figure out how to do that before we program it into a computer. If we want to do body mass index, we need to know the formula before we tell a computer how to do a formula. So the question is, if I was to give you a program of 10 or so lines, can you determine if it halts? And again, I'm not going to do any tricks. They're going to be completely understandable programs. And of course, this is assuming that a computer works properly. If a computer doesn't work, then there's no point in this whole talk. We're going to ignore the fact that an int maxes out at actually 2 billion, because it turns out that there are ways around that we haven't seen. So I'm going to show you a couple examples on the next slide. And for each of these, I'm going to say, can you and I, humans, determine if the program halts? So for each of those, I'm going to assume that that code's in a main method in a class somewhere, and then I'm going to, I'm just going to shorten my print line statement so it fits. So, that being said, looking at program 1. System.println, Alan Turing, system.println was a genius, system.exit. I think we could all agree that if we look at that, that will definitely halt, right? Because the print statement does something, the next print statement does something else, the exit stops, right? It halts after that third line there. Yes?
But the parameter into when you push system.exit.
The question was the system.exit empty. You can actually call system. It's overloaded, so you can call it with an int parameter or without an int parameter. So you don't actually have to have an int in there. So I think we could all agree that this program halts. Does anybody disagree? Okay. What if we were to look at this one? For n equals 0, n is less than 10, n plus plus, print out n. And I think we could all agree that that will also halt. It'll go through 10 times and, excuse me, it'll go through 10 times and eventually halt. Right? Does the print statement 10 times. Now, of course, one thing with the halting problem is, sure, you can run the program and wait to see if it halts, but I could easily write a program that waits 1 billion years and then halts. It does eventually halt 1 billion years from now, but you obviously, in our lifetimes, we can't sit there and wait for it to terminate. So, third program, while true, print out hello world, system.exit. I think we could all agree that that actually won't halt. That is going to loop forever because the print statement is inside the while true loop. So we don't know if that will halt. I'm sorry. We do know that it will not halt. That will loop forever. And I think we can probably all agree on that. Here we have int x equals 10. While x is greater than 0, and of course 10 is greater than 0, it's going to print out hello world. And instead of decrementing x, which is probably what was intended, I increment x. So then it's 11. It prints out hello world. 12, 13, 14, 15. Here the difference is that that plus probably should have been a minus. If it was a minus, it would eventually halt, but it's a plus. So this is going to print out an infinite number of hello worlds. And I think we could also agree that that will loop forever. So the 2 on the right loop forever, and the 2 on the left halt. And these are all fairly simple programs. So that being said, here's question 2. It's the same as question 1. I just want to see if anybody's answer has changed. Apparently there's 7 people that aren't voting this time around. Up 5. Okay. So pretty similar. So I'm going to show you another program, about 10 or so lines. Before I do, I want to talk a bit about mathematical theory. A perfect number is a number whose divisors, not counting itself, add up to that number. For example, 6 is a perfect number. 1 plus 2 plus 3 is equal to 6. Technically, 6 is a divisor of 6, so 1 plus 2 plus 3 plus 6 is 12, which is twice 6. But essentially, all the divisors other than itself add up to that number. 28 is a perfect number. 1 plus 2 plus 4 plus 7 plus 14 equals 28. And those are actually the first 2 perfect numbers. So that is, obviously, we're not adding 28 to that as well. And perfect numbers is something that's been known since antiquity. The ancient Greeks actually knew about perfect numbers. And these are the first 10 perfect numbers. And we don't know how many there are, but we do know that there is at least 10 of them. It could be that there's an infinite number of them. But you'll notice that the last one there was a whopping 54 digits long. That's a pretty big perfect number. But if you actually do all the divisors of that, it will add up to that. It will add up to that number. Okay. I'm sorry? You know, the question was, did a computer find that out? I'm sure they used a computer to do it. I doubt they started counting from 1 and started spitting out all the perfect numbers. I actually don't know enough of the perfect number theory to figure out exactly how they figured it out. They probably have some shortcuts. I mean, as opposed to people just sort of randomly guessing, for sure. So all known perfect numbers, certainly those 10 and all the other known perfect numbers, are even. It is an open problem, meaning it is not yet known if there are any odd perfect numbers. Maybe there are, or maybe there are not. We, as you know, civilization and the mathematicians have not yet proven one way or the other whether or not an odd perfect number exists or whether or not an odd perfect number does not exist. It's generally believed that, well, at least my suspicion is that they probably don't, but I'm not a mathematician. So yes, if you want, you can actually look at the next couple perfect numbers following that link. So all we know is that odd perfect numbers are even. All known odd perfect numbers are even. We don't know if there are any odd perfect numbers. So the question is, will this program ever halt? So let me go through and explain this. Essentially, this program is going to loop forever until it finds an odd perfect number. So So we start out with n is equal to 1, the first odd number that we're only talking about positive numbers here. And every time the loop goes around, it's going to add 2 to that. So 1, 3, 5, 7, 9. It's eventually going to go through all odd numbers. We're going to count the sum of the factors. This for loop goes through all possible numbers. So let's say we're talking about 9. That for loop is going to go 1 through 8. And what it's going to do is it's going to see if any of those numbers that we're looking at evenly divides it, then it's a factor, and we're going to add it up. So here, sum of factors, when this for loop is done, is going to contain all the possible the sum of all the factors of that number. And if they are the same, meaning if we found a perfect number, then it's going to break. Now keep in mind that we're starting at 1, we're incrementing by 2 each time, so we're only looking at odd numbers. And this will break only if it finds an odd perfect number. Whoops. Will this program halt? Can anybody here tell me for sure, one way or the other, whether or not this program will halt? The best mathematical minds in the world can't, because we don't know if we as human mathematical society do not know whether or not we will hit any odd perfect numbers. And this is a relatively simple program, right? It's only 10 lines, yet it's not known if this program will ever halt. We as humans, I'm multiple humans, but me as multiple humans cannot figure this out. Question?
But when you have while and then parentheses true, it is going to not halt?
Well, this break here will cause it to exit the loop. Right? So let me actually erase all my writings. Yes, that will always go around and loop it again, but remember that a break will cause that particular loop to terminate. So the fact that, basically we go through, we figure out all the sum of the factors. If the sum of the factors is equal to n, then we're going to break. So anytime we hit that line, then this program terminates. So it might be possible for this to halt, right? If we find an odd perfect number, then this program certainly would halt. Other questions? So we as humans can't figure this out. The question is, can a computer figure this out? Which leads me to the next one. Do you think it's possible to solve the halting problem? Meaning, can I write a computer program that could take in any Java program, such as the one previously, and print out true or false, it halts, or it loops forever? Okay. So as we can see, the general trend has been, at least from the last to this, is that fewer people think it's possible to solve the halting problem. As it turns out, and this is obviously not something I expected you to know ahead of time, right? But it turns out that if a human cannot figure out how to tell if a program halts, a computer can't figure it out either. We as humans, there's no way that we as humans yet can tell if that previous program halts, so we can't program a computer to do that either. So as it turns out, it's impossible to write any such check-halt method. Meaning, I am telling you without a doubt, and I'm going to show you why in a minute or two, that it is not possible for you, no matter how good a computer scientist you are, to write such a method that will tell for sure whether or not any Java program will halt. You could write in and tell whether some kind of small, rinky-dink programs will halt, but not whether any program will halt. So the question is, of course, how do we go about proving this? Well, this is the proof that Alan Turing showed in 1936. He showed that it's not possible for a computer to do this. So consider this program P and input I. Right? Whether program P is the odd perfect number search on the couple slides ago or anything. And again, suppose that we had, for sake of argument, this is called the proof by contradiction. I'm going to assume that I have such a oracle.checkhalt method, and then I'm going to prove that it actually can't exist. So I'm going to test to see if that program with that input, sometimes abbreviated P sub I, will actually halt or loop forever. So keep in mind, a program is a series of bits. A program is something on a disk, some sort of file that has, characters, returns, that sort of stuff. And if you are calling P sub I, then you can actually use the program as input as well. And it's certainly possible. Why we want to do this, you'll see in a minute or two. But it's certainly possible to call check halt of P comma P. What that's saying is I'm going to use, given some program that I want to test, to see if it halts, I'm also going to use that program as input to the program. Maybe it reads in a file and spits it out. Maybe it counts how many characters are in it. Who knows? Maybe it doesn't use any input at all. But if the program is just a file on the disk, if P is just a file on the disk, and I is just a file on the disk, we can certainly have them point to the same thing. As long as P is a program, we can use the particular bits in that file or the contents of that file to also use it as the input to that program. So consider this program. Blah, 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 blah. So public class test and, our main method. Here we say if oracle.checkhalt. Now, this is class test, so it's in a test.java file. So when I say test.java, the particular program I'm testing to see if it halts is this program right here. And I'm also using that program as input. And if it tells me, if checkhalt, using this program that we're looking at right now, both as a program and input, if it tells me it loops forever, I'm going to halt. If it tells me that it halts, I'm going to loop forever. So remember, checkhalt just returns a Boolean. And that particular Boolean is either going to be, if it's true, then it's telling me it loops forever, so I'm going to do the opposite. I'm going to halt. If it tells me it halts, that's the else, then I'm going to loop forever. And that's my very small looping forever. That'll just hang indefinitely. So all this does, this particular program does, is it calls my oracle.checkhalt method, finds out if it returns true or false, and it does the exact opposite. In particular, notice that the particular program I'm sending in is the program we're looking at, and the input I'm sending in is also the program we're looking at. And I think we could all agree that while perhaps a bit odd, this is a valid program. Right? Assuming, of course, we have the oracle.checkhalt method, this would certainly compile and run and hopefully do what it's told. Okay. So this is a somewhat condensed version of that said program, right? The main method is squashed, et cetera, but it basically does the same thing. If this says that it loops forever, I'm going to halt. Otherwise, it's telling me it's halting, I'm going to loop forever. I'm basically doing the opposite of whatever the program, whatever oracle.checkHalt tells me. So it turns out if I was to run this program, there's only two possibilities, two things that can happen. Either it halts or it loops forever, right? Because this is an if. This check halts, and maybe it returns different things each time, who cares? But this this method here is going to give me a Boolean, either true or false, no other possibilities. And either it's going to halt or it's going to loop forever. So let me look at each possibility one at a time. Let's first assume, for whatever, we're going to first assume that it halts. If it halts, then oracle.checkHalt had to return true, right? Because we only get to this part of an if oracle.checkHalt returns true. If oracle.checkHalt returns true, then it's telling me then that test.java loops forever. But we know test.java doesn't loop forever because we've assumed that it halts. Let me go over that again. I'm assuming that it halts. So for the next minute or two, we can say that it definitely halts. I'm going to assume the opposite down here in a minute. So I'm assuming that test.java halts. If it halts, that means oracle.checkHalt must have returned true in order to get to that part of the if statement. If oracle.checkHalt returns true, then it's telling me that this program loops forever. But we know it doesn't loop forever because that was our assumption. We've already assumed that it halts. We've reached a contradiction. It's not possible for this program both to halt and to loop forever. So let's look at the other possibility. Let's assume, for whatever reason, that this program, when run, loops forever. And loops forever means it must have gotten to the else part of this if statement. If we got to the else part of the if statement, then oracle.checkHalt must have returned false, because that's how you get to the else part of an if statement. So checkHalt returns false, which means that this thing halts. Because remember, Boolean false, as far as this method is concerned, means that this false. So we've assumed that it loops forever. Therefore, this returns false, meaning it halts, which says that this thing halts. But we know it doesn't because we've assumed that it loops forever. And yet again, we've reached a contradiction. So no matter what you assume, whether this class test returns true or false, meaning it halts or it loops forever, because of the particular kind of strange way this thing was created, if oracle.checkHalt is telling me that this program loops forever, then it's going to halt. And if oracle.checkHalt is telling me that the program halts, then it's going to loop forever. So this is in effect going to do the exact opposite, and it is not possible for anybody, human or computer, to determine whether or not this program halts. Because if you say it halts, then it's going to do the exact opposite and loop forever. And if the oracle, says it loops forever, then it's going to do the exact opposite and halt. How are we doing with that? Okay, I actually think that's fairly good. This is actually fairly advanced theory, and that's actually better than I was fearing. The thing I want you to take away from this is one way or the other, we're able to reach a contradiction. If you were to somehow write a check halt method, and I was to feed it in this exact program, it would cause your check halt method to not work. Because your check halt method says one thing, it loops forever, this program is going to do the exact opposite. And if check halt says it loops forever, then it's going to exit. So obviously check halt can have said it loops forever because it's exiting. And if check halt says it halts, then it's going to loop forever. And obviously you have a contradiction because check halt is saying one thing and this program is doing something else. And the thing I want you to take home from this is that it is not possible for a computer program to be written that determines for sure whether or not some program P with input I will ever halt. We can do it with a subset of programs, like really small programs that don't really do much. But for a full-fledged programming language, and there actually is a formal model for how you define a full-fledged programming language, it's not possible to do this. Right. So why do we care about this, you might ask? Well, it turns out I can easily show you that it's possible to write a computer program to do something by showing you that example, right? I showed you it's possible to write a computer program to compute the body mass index. I showed you the program. That was my proof, right? You can show something exists by just showing that particular program. But how do you show something can exist? This was the first time any algorithm, and this was before programs existed, 10 years before computers existed, any algorithm was shown that could actually never exist. Right. Alan Turing back in 1936 is the one who showed this. So ENIAC came out in the mid-1940s. That was at University of Pennsylvania, computed artillery tables. It was the first digital programmable computer. But this was 10 years before that. And in fact, he laid a lot of the groundwork for modern computer science. And the top computing award, which is probably analogous to the Nobel Prize for Computing, is actually named in his honor. It's called the Turing Award. So that is why we care about the halting problem, because it was the first and one of the few algorithms that actually has been shown that can never be done by computers. So computers can do a lot of things, but there are some things that they just simply cannot do. This is one of them. And it's probably true that humans can't do it either. Yes?
Much harder to prove that a program can never exist.
Right. So here I've proved that this check halt program can never exist. Right. So, I mean, it's easy to show that a certain program exists, right? If I was to show you, I could prove to you that the body mass index program exists by showing you the code and running it. But how do you prove that that check halt program can never exist? And that was the contradiction we reached 2 slides ago. And that's what it's extremely difficult to do. Whew. Okay. Questions before we get onto the property motivation for today? How many people, just by show of hands, how many people feel they have a general idea of the halting problem? Okay, good. I'm seeing a good number of hands. Effort. Hard work never killed anybody, but it is illegal in some places. So in August of the reason that it's France, Paris, and the Eiffel Tower is in August, most of France just takes the entire month off, which I think is great for relaxation, but it doesn't do much for their GDP. Worth. Just because you're necessary doesn't mean you're important. Destiny. You were meant for me, perhaps as a punishment. Quality. The race for quality has no finish line, so technically it's more like a death march. Okay. So that's all I'm going to be going over in terms of this slide set, as you could probably tell from the bright green slide. There are a couple more examples dealing with loops in the slides. We go over things such as triangle counting, and then a ways later we go over number counting. You can look through that if you feel you want more examples, but I'm not going to spend more time on that today. So brings us to chapter 5. We have used many methods. we're now going to start writing our own methods. And that's really the basis of Chapter 5. We're then going to move into Chapter 6, which is writing our own classes. And, of course, we need to be able to write methods to write our own classes. So we've seen a whole lot of stuff dealing with computers. I mean, with Java programming, right? We've seen loops. We've seen conditionals, if, switches, if else if. Seeing ways to get input, to produce output, create variables, create classes. What we're now going to do, excuse me while I inhale my cough drop. What we're now going to do is start getting into the object-oriented part of Java. We're going to start creating our own classes and creating our own objects and using those to be able to do more and bigger and better things in our programs. So the idea with object-oriented programming, as to a certain extent you've seen and will continue to see throughout the rest of this class, is what you do is you create objects. Maybe there are objects like a string class that exists in Java, the SDK, or maybe there are classes that you've just created yourself. With the course project, which again we expect to be the Oregon Trail, you're going to be writing a lot of classes and then creating objects of those classes. Blah, blah, blah. I don't think you care too much about that. We've seen a whole slew of classes. In particular, I guess we haven't seen big integer, but we've seen a bunch of others. We've seen vectors, we've seen rectangles, we've seen scanners, and we've seen system, right? System.out.println, system.in, system.exit. So we're going to be getting to classes shortly. That's Chapter 6. But first, we need to talk about creating methods. Methods. So we've seen a number of methods before. And you will hear different people call them different things. Methods, functions, procedures, subroutines. The difference between them is you'll see when you get beyond cs101. For example, to find the sine of an angle from the math class, I call the sine method, and I give it an angle. In this case, I'm doing 90 degrees, and this pi over 180, if you remember from geometry, is how you convert degrees to radians. So here I'm telling it the angle as the parameter, whatever that works out to be. It's about pi over 2. And that's a parameter to sine. The sine method then knows how to go forward with that, and it tells me that the sine of 90 is 1. And then that value is stored into the angle sine variable that's presumably been created. System.out.println, hello world. Here I'm giving it a string, and that string is going to be printed out to the screen. The card.getBlackjack value, oh no, we haven't seen get value. It's just like get value, but it's specifically for blackjack. So we're going to start creating these methods ourselves. In particular, many of these, of course, return a value. We recall math.sine. It's giving us a value, 1.0, which is the sine of 90 degrees. And that value is stored in the angle sine variable. This card.getValue is giving us an angle. A return value, 2, 5, 10, whatever it is. And that's stored in the variable value. Notice that the println method doesn't give us a value back. It does not give us a number or a string back. It just goes and does whatever it wants to do. So some of these methods, such as the first and the third, I will make it to the end of lecture. The first and the third actually give us a value back. Middle one, not so much. In particular, when we're naming methods, we do the same name as variables. We take, if we have many words, we take all of them, we squish them together. The first letter of each word is capitalized. First letter of each word is capitalized. But the very first letter is lowercase, such as get blackjack value. There, the B and the V are capitalized. All the words together, et cetera, et cetera. Same way that we like to name variables. So here's our first take at using methods. What we do is we read in some input somewhere. So we read in some integer into the program. We store it in a variable called value. And here we're saying if value is equal to 1, I'm going to call the valid value method. Notice that I have not said from a class call the method or from a object call the method. We're going to get to that in a bit. But for now, what we're doing is I'm saying I'm going to call the valid value method. If value is 2, it's also valid value. If it's 3, it's invalid. If it's 4, it's invalid. Otherwise, it's valid. Okay, it's probably not the program that you would most want to write, but it shows what we're trying to achieve here. In that 3 of these if-else-if cases, 1, 3, and the ending else, all will call the valid value method. 2 of these call the invalid value method. Java knows it's a method because it looks at the name, but really it sees the 2 parentheses there. These particular methods don't take any parameters, but Java sees that the parentheses are there, so it knows that you're trying to call a method. And here we have the invalid value method. And there's a lot going on here. Let's first look at this. We print out, you've entered an invalid value, the program will now exit, system.out.exit. And here we have valid value. Congratulations, you've entered a valid value, you're a winner, system.out.exit. Or, I'm sorry, system.exit. And this is the definition for these 2 methods. And you notice that there's a lot going on up here as well. It looks kind of like the public static void main string args. Indeed, public static void main string args, that's also declaring a method. But here, so I'm ignoring what public and static is for now. We're going to get to that in a week or 2. I'm going to tell you all about public and static, more than you probably ever want to know. But for now, everything's public and everything's static. This is the name of the method, valid value or invalid value. Right, so that's the name of the method. This here tells Java that there are no parameters. There are obviously methods that do take in parameters, but these particular methods don't take in any parameters. Lastly, we have this keyword void. Void means that this particular method does not return a value. We're going to talk all about return values in a bit. Probably not today because I have about 3 minutes left. But we're going to talk about all return values in a bit. But void means it does not give any value back. Like the print line statement, it doesn't give you any value back. So we can take, I don't want my things. We can then look at that particular code, and that's the entire class. And you'll notice now that this public class methods1 contains 3 things now. In addition to the main method, which everything's contained up to now, it contains the invalid value method and the value method. So when I call valid value, it's then going to start executing this method. Wait, I have another minute or 2. So let's quickly trace. Yeah, I have a minute or 2. Let's trace through this. Scanner, standard equals new scanner, creates my scanner. We read in a value. I'm going to assume that I've read in 1 because that's all that really fit on this slide. If value is equal to 1, it is because that's what I assume I've read in, then I'm going to call this particular method. What happens there is Java will immediately start executing at the beginning of that method. And it will then print out the 3 lines and exit. Exit immediately terminates the program. But the thing to keep in mind here is that as soon as I hit this method call, I immediately start executing at that method. At any given point in time, there's only one point in the program that Java is executing. In this case, once it hits this valid value method call, I start executing in that method. Blah, 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 and then it exits. Okay, a couple things to remember, and then you're free to go on time. All methods are static and public. We will see why they're static and public later, but for now, they're all public and they're all static. None of these return a value. They're all void. We're also going to see all returning values in a minute, in a while, and none of them take in any parameters. That's all I have. I will see you. There will be class on Wednesday, but I will see you on Friday.